I'm sure, like most CS294s, this has an extension too, right? CS294?
73.
73.
But as of next time it's taught, it will be CS266.
Oh, that's going to get a permanent name.
Gets permanent
number. Sorry, yeah. Cool.
Name will remain the same. Software engineering for scientific computing.
But that's probably better than the 5. You probably don't need 5-digit encoding. It's not. This is not a telephone number of a medium-sized city. Pretty good though. I'm actually pretty excited about these slides. I might use these later for Graph Plus tutorial lectures.
Good.
Some of them, maybe.
Glad to hear that. Also, I'd like to get a copy of them.
Sure, always. Do you post it somewhere?
Yeah, I'll post it for the students, both on our website and in the repo.
How do you keep it? Class website?
Yeah, there's class website.
I couldn't find it when I Googled, but must be linked from somewhere. God knows.
Yeah, it's linked from somewhere. God knows. We keep a low profile here.
No, I mean, I sometimes couldn't find my own class's website without, going to my bookmark. So it's not a surprise. Okay, it's 11:10, so I'm Aydın Buluç. I'm staff scientist at the Lawrence Berkeley National Laboratory. Since you're taking the class from Phil, you probably know where it is. And I'm also an adjunct assistant professor here. So today I'm going to talk about graph algorithms, graph motifs, meaning that the building blocks that you use to write graph algorithms efficiently. And I'll put a bit of parallelism because, in my view, one of the main reasons of using these motifs to write algorithms, especially for problems like graphs, is the parallelism. We don't really have the kind of luxury like dense BLAS has, where you can exploit the memory hierarchy significantly, that any kind of BLAS primitive, even on serial machines, have a significant advantage than your hand-coded algorithms. In our case, most of it comes from proper exploitation of parallelism. So that's why it's kind of necessary to include that. And I'll even use real code examples. So what is a graph? A graph is some data structure, abstract data structure that you'll find a lot in computer science textbooks. It is formally defined over a set of vertices, also called nodes, and edges that connect those vertices. In the simplest terms, standard graph definition means edges connect 2 vertices at a time. There are extensions to that called hypergraph, where the edges are defined over any number of vertices. So people also call them nets, but we're not going to talk about them. They're usually useful for partitioning for load balancing and some other high-level representations used in data mining. There's a couple of definitions, but not significantly important for for this class. The diameter is kind of useful, which is the maximum number of hops between any 2 pairs of vertices. If you're exploring this graph 1 hop at a time, which is usually what the parallel traversals do, that means this is the fastest you can do if you have infinite number of processors, because there's a sequential dependency there. So that's why it usually comes handy what diameter of the graph is. And it's really significantly different from graphs that come from physical simulations, where the diameter is typically large, on the order of square root of the number of vertices. And if you're looking at graphs like social networks or biology, they're usually small. So there's pros and cons on that, which I won't get into.
So I need to remind you, this is being video captured.
Yeah.
So if you want to point at anything on
your
slides, use that.
Mouse, yeah.
Thank you.
Good point. I forget, even though I've been reminded that lots of times. The edges can be directed or undirected. Undirected means just tells you that there's a relationship between vertex A and vertex B. It doesn't say what direction it is. There can be ways, attributes. You can put pretty much anything on edges and vertices. But so why do we do this thing? Why do computer scientists and computational scientists care about graphs? Every time you open your Waze or some sort of Google Maps, that's an old picture, there is some graph algorithm that computes the shortest path. It's not the typical graph algorithm you find in the textbook if you're curious, because what's really special about a road network is it's almost planar. There are some bridges that cross each other, but for all practical purposes, it's awfully close to planar. And the algorithms to compute shortest paths, there are specialized algorithms that will run this thing way, way faster than your textbook Dijkstra or whatever else. And for fill, and if you're curious, the way they do it is something that looks like Gaussian elimination. You extract, you kill the vertices one at a time, and there doesn't happen to be a big fill because it's almost planar. They didn't know about that connection for a while. And the internet and the World Wide Web, so the web search and crawl is some sort of graph traversal. All these ranking, even though there has been many algorithms, and the fact that we don't know exactly what PageRank is these days, what Google uses these days, doesn't matter. It's still a graph algorithm. Clustering, document classification, and finally, when packets are routed in the high-level internet topology, it's the standard Bellman-Ford algorithm still is in use for finding the shortest paths. What we do at the lab, the Berkeley lab about graphs, is a little more intricate, and it's going to take a little more time for me to explain. One of the workhorses of scientific computing is solving a system of linear equations. AX equals B. So you know you're given A, you know B, you don't know X, you're trying to solve for it. Right? If that A is sparse, usually the way the algorithm proceeds, unless it's symmetric positive definite, maybe too much information, is you have to do pivoting in runtime to avoid any kind of crashing. So if you have 0 entries on your the mouse, if you have 0 entries in your diagonal, that means if you don't pivot, you're certainly going to crash. Even if you have all non-zeros in your diagonal, all these dots actually mean a non-zero. If empty slots is a 0 in this picture. Even if you have some non-zeros, but if their values are small, you probably have lots of numerical issues down the road. So how do you solve this problem? Well, in serial, in shared memory, you can pivot in runtime and choose the biggest entry. In distributed memory, it's really expensive to do that. So what people do is, I'm going to pre-permute this graph, like in the right case, in this matrix, sorry. So the diagonal entries are heavy, meaning they have large absolute values. Okay, and it turns out the way to do that is to view this matrix as a bipartite graph. Bipartite graph means it's a graph that you can separate it into 2 pieces. Doesn't need to be balanced. In this case, it is. Let's say n and m pieces. And all the edges are between one piece and the other piece. There are no edges within any of the classes itself. So, and you try to find in this bipartite graph a matching with maximum weight, a perfect matching with maximum weight, meaning that all the vertices are matched. So what is a matching? It kind of looks intuitively is easy to see. Right? Everybody on the left is trying to get matched with someone on the right, and every person or every vertex can be matched to at most one other vertex. So it's not the formal definition. The formal definition of matching is a subset of edges such that the endpoints of those edges are never intersecting. So they're independent edges. That's the definition of matching, but we're not going to talk about it today, so it doesn't matter. And graph partitioning is often used for load balancing in scientific computing. Here you see any kind of, you can model your computation pieces as vertices and their communication between them as edges, or their dependencies between them as edges. And what you're trying to do is, A, try to find a load balance partition of this. B, try to minimize the communication between them. So that's a commonly used problem. There's a whole lecture about this in CS297. But at this current 21st century, you would be better off just using an existing software than reinventing that wheel. Data analysis. Lots of scientific problems have fairly what we call hairy graphs, where there's lots of attributes, there's different classes. Similarly, in social informatics, what do I mean with different classes? I think it's easy to talk about Facebook again. When Facebook modeled its infrastructure as a graph, there was a Facebook graph concept several years ago. I don't know if they still use it. It made it to the news. It's like not only every person in the Facebook is a vertex, it's every page is a vertex. So there's a heterogeneous collection of those. And edges are also heterogeneous, right? It's just not between your friendship. There is another connection, it's following relationship, or it's whether you like that page relationship. You have to encode what kind of edge it is. So that's why I say it's heterogeneous. It's lots of attributes. And in things like astrophysics and bioinformatics, the edges have some uncertainties associated with it, you don't know exactly how confident you are for that connection.
What are the edges in astrophysics?
That's a good question. I actually don't work on that. I can tell you about bioinformatics. I will one day give a more informed answer on that next time I get it. And here's a machine learning. Lots of machine learning problems use graphs and subroutines. Here's one that might be interesting. This is a manifold learning so-called algorithm. Also probably easier to describe it as a nonlinear dimensionality reduction. So I assume your points are not in a linear space, but in some sort of Swiss roll. And I don't know how contrived this example is, but this is how they motivate it. And so how do you do dimensionality reduction? You first need to get the distances straight. And the distance between these the distance between these two dots on the figure A, you can't use Euclidean distance because they're not exactly close to each other. It just seems like they're close. They are laying on a different space, and you have to find essentially first a graph of k-nearest neighbors so that it doesn't put these normally unrelated entities close to each other, so there's no connection to that. It looks like it's infinity. Now in that k-nearest neighbor graph, you can find the shortest path between them. That's going to be your correct distance. And then you're going to continue running your standard dimensionality reduction algorithm. And we're going to talk about how to compute all pair shortest paths really fast in a couple of slides. And my notes in this slide tell me, to my surprise, that in fact it is the bottleneck in this process. And I think this is my final motivation slide in bioinformatics. So you might have heard the genome assembly, genome sequencing. When someone sequences the genome of a new species or just resequence a known species with significant divergence from existing reference, what they do is called a de novo assembly, meaning that from scratch. The input to these things, what the sequencer generates, essentially is short reads. Short can be 100 base pairs, 1,000 base pairs, 10,000 base pairs. It's still way shorter than what we're talking about. For example, in the human case, we're talking about 3 billion base pairs. So it's just, as if you have a book and you shred it to little pieces, now you're trying to put together. And depending on how short it is, there are different abstractions on how to computationally describe the assembly process. But both of them, there's overlap graph concept, there's De Bruijn graph concept, is some sort of graph abstraction. And then you try to find connected component or even more complex things on this graph. And these are pretty big. That's why we actually use parallel computing sometimes to them. This is an example from a problem that I helped assemble. It's a wheat genome, the standard bread wheat. So if you look at its graph of De Bruijn graph, you're talking about 26 billion unique vertices are in there. And brain, I don't know how this is going to go scientifically in the next couple of years. But the standard, one of the standard ways to analyze the brain connectivity is to weave it as a graph and look at its properties. And here, each vertex can be anything you could measure, depending on how good your technology of measuring the brain is. Of course, the neuroscientists would like to get it all the way down to single neuron. I don't think they have a way to do it yet, but they fantasize. So these things can happen. And we'll see how much of a challenge it will be when that happens. So that's all about many applications. I will go on to a little more technical stuff. I assume no questions so far. But if you do, just raise your hand. Graph representations. How do you represent a graph? The textbook way of representing a graph is an adjacency list, especially if it's sparse. What does that mean? This is a 4-vertex, very simple graph. For every vertex that has an outgoing edge, you keep a list of those edges. Just look at 4, for example. 4 has 2 because it has an edge to 2, and it also has an edge to itself. So that's all linked to each other.
They've implemented CSR for sparse matrices.
Yeah, great. And in fact, it turns out CSR is the right thing to do as opposed to, if your graph is static, if there are not a lot of insertions and deletions, this is not the greatest data structure. Why? Because list is cache unfriendly. Every time you hop to the next element in that list, you are making potentially a cache miss. And there's really no need to, for such a small data, you don't really need to put an 8-byte pointer here either, even if you're not doing a cache miss. So compressed sparse rows that represent sparse matrices, essentially you can weave them as packed adjacency lists. That's what it is, and you'll see how familiar this is. All that happens is this guy gets packed together and stored in separate arrays of adjacencies and weights. I call them the graph name, but really these are row pointers, column IDs, and numerical values in the CSR data structure. So that's probably the fastest thing to store a graph in a shared memory or a single memory space. Well, in distributed case, things get a little hairy. And the answer, distributed memory means you have a bunch of processors that do not share a memory space. Assuming everyone is familiar. Then you have to figure out how to distribute your graph. Well, the first question is you can ask yourself, do I really need to do that? If my graph is small and my computation is expensive, like I'm finding some sort of traveling salesman problem, I probably don't want to distribute my graph. I'm not going to be able to solve anything bigger than a couple of thousand anyway, so I might as well replicate it, all the graph, and then the computations will be distributed and they will share some progress information about themselves. That's fine, but for a lot of graph problems where it's not expensive, like traveling salesman, you have to distribute the graph because now you can solve really big problems, and that's the main purpose of parallel computing. The standard way of thinking about it, you give me a graph, what do? I say, you give me n vertices. Well, I'll divide it into p. P is the number of processors. And the first processor will get the first n over p. Second processor will get the second n over p. Great. And that turns out to be the standard way people first think about these things. And you'll see a lot of load balancing issues. And I'll show it in a picture maybe later. But I can describe it right now. What does this mean? When you divide the vertices into processors, all the outgoing edges of those vertices go together to that processor, right? So imagine Twitter. There are some entities that have a lot of followers. Usually the president gets a lot of followers, right? Who gets a lot of followers? There's some people like that, really famous celebrities. It's not a lot of people, though. This is the problem. So if you're trying to distribute this graph into 10,000 processors and you have only 100 really high degree vertices, degree means the number of connections, well, there's no way to get good load balance on that. You cannot divide 100 heavy items to 10,000 pieces. So one-dimensional decomposition, what we call a vertex partition also, the way I described, you assign vertices to processors and all their edges go to them, has a load balance problem for graphs with skewed degree distributions. And how do you solve that? You do a two-dimensional decomposition. What does it mean? It doesn't mean much if you're just looking at this graph picture, and you would probably not be able to figure out how to distribute this in a principled way to a 2D process grid. But it's actually pretty obvious if you look at its matrix. Here, what does it mean with this matrix? So the second way of storing graphs that I didn't tell you about is adjacency matrices. Well, it means for every edge in the graph, I will have an entry, aij, for example, in this matrix. We'll say that there is a vertex, there is an edge between ith vertex to the jth vertex, and here's the value. The trick here is never to use a dense matrix representation to store this. I'm describing this in the figure as a dense matrix, but the way you store it is still CSR. So just conceptually to see what's going on, I'm drawing it in a 9x9 matrix. In reality, it's all CSR. But this helps you to see how you would divide this into 9 processors laid out in a 3x3 process grid, right? You're just going to checkerboard, partition, and if you have load balance problems, now it's actually easier. If you randomly permute the names, the vertices, and it's not going to change the graph structure at all, because the graph will stay the same. You're just renumbering the vertices, but it will help you with the load balance significantly. This, no matter what graph you throw at me, if I randomly permute the vertices, I haven't seen a case where the load imbalance was more than 5%. This pretty much always solves, because even if you have really dense rows or columns, there's 2 dimensions to cut it. Okay, so that's all about the data structures and storage. Not too much details, but I think you'll get to see it as we go in about case studies. So I have a lot of case studies, but there's a reason for that. They highlight different primitives, and for each case study, I'll highlight one sparse matrix primitive that you can just use to implement it.
So just a quick question back to like the load balancing. So
Yeah.
you're saying that if you permute them, you're not getting much randomly permute the numbering kind of the ordering of the grid. You're not getting any gain in load balancing.
No, I said the opposite. So if you give me a graph, even if it's very skewed, meaning that all the non-zeros are kind of clustered in, let's say, top left corner, and if I renumber the vertices, which in the matrix word just means a symmetric permutation, it will scatter around nicely, and the load balance will be close to perfect.
Okay.
That's what I'm saying.
Okay.
That is not the case in one-dimensional decomposition. In that case, if you have a skewed degree distribution, no matter how you permute, there will be some matrices that will stay load imbalanced.
Yep.
All right. Breadth-first search, the most fundamental thing. But first, graph traversal. If you open a textbook, they will say there are 2 ways to traverse the graph. There's more than that, but there's 2 fundamental ways to traverse the graph. The first one is depth-first search. And here, the way you go is you visit one of your neighbors, and then you give the control to that neighbor. So before you explore your other neighbors, you basically say, OK, the first neighbor I explored, now you go explore your neighbors. And since everyone does the same thing, first the graph is explored as deep as possible, and then it all collects back. And the way to write this in code is very trivial, this 5-line code. In fact, this pre-visit and post-visit are just, what are you going to do? You don't even need to have those. It's actually a 3-line recursive call. Don't implement it this way. It's going to blow up your stack. It's a stack overflow. But for pedagogical purposes, it's great. So it tells you how it goes depth-first search. First, you explore 2, right? Before you explore 5 or 7, which is your other neighbors, you will give the control to 2 because of the recursive call here. And then 2 will start exploring. So that will go continuously that way. And the way I numbered this thing, there are 2 different numberings. This is one particular one called pre-order, I think, vertex numbering. Do you order before you call the recursive function, or do you call after that? It changes it, and some algorithms like one ordering or the other. Why is this so popular? This is a very memory efficient way if you implement it correctly in a serial machine. And it's sometimes magical. Like there's very complex algorithms that have been implemented using depth-first search that amazingly runs in linear time just because of the backtracking properties of depth-first search. See, like once you start exploring this thing, at some point it starts this backtracking process, and it's very peculiarly advantageous to generate some novel algorithms that's going to run in linear time. Examples is biconnected components that doesn't look like it's going to be strongly connected components. None of those looked actually stuff that would run in linear time, but depth-first search enabled that. There's a very nice old paper by Bob Tarjan that says depth-first search and related graph problems, probably in 1974, something like that. Anyway, the problem is, so there's a concept called span in parallel computing. A better way would be a critical path. If you give me infinite number of processors, how fast I can run this? And another way to look at it, what is the bottleneck in the dependency structure? So it's order n. No matter how many processes you throw at this problem, it's going to take time in the order of a number of vertices. If you have a sparse graph, meaning that you don't have much parallels. So it's inherently sequential. That's why it's not used a lot in high-performance computing or any other parallel computing. Instead, you use breadth-first search, which is also actually pretty nice. It doesn't have some of the magical properties, but it's linear time, and it's much more parallelizable. Here, you do the opposite. Instead of giving the control to the first neighbor you visited, you first visit all the neighbors you have, and only then you continue. So all the vertices that are 1 hop away from you gets explored first, and then all the vertices that are 2 hops away from you get explored after that, and so on. And this is what you need to do. You do not really need to keep a stack. You can keep any vectors, data structure, linear data structures for the visited vertices. This is one of the problems. I'll come back to the end of the lectures. There are some artificial constraints enforced in these graph algorithms in your textbooks, which you will be relieved from once you think of them in the language of matrices. But the point I want to make on the slide, which is a strong one, is it's a very important building block. For many parallel graph algorithms, at the end of the day, you're doing breadth-first search as a subroutine. And we've done this successfully in bipartite graph matching that I described earlier, maximum flow, strongly connected components, not so strongly connected components, and between centrality, which I will describe later. And here is how you breadth-first search using just matrix vector operations. So the main point I want to make is I'm going to start traversing this graph from a vertex called 1. And I'm going to do just multiplication with this sparse matrix, A transpose. It can be A, then you will be multiplying on the left. I use A transpose. Simply, I like column vectors, like anyone who likes linear algebra, they like column vectors. And then you generate a vector that has only one non-zero, which is your starting vertex. And you'll number it with that index. Whatever the index, it becomes the value, it's 1. And the second important thing is I'm not doing this multiplication in the standard field you learned in linear algebra. For every scalar multiplication, I'm just going to select the second operand, whatever it is. If I'm multiplying A times B, I'm just going to return B. Okay, for every addition, breadth-first search will be correct whatever I do, but to stay deterministic, I will return the minimum. Okay? This looks contrived, but it's not. This is just a different algebra. The data access patterns are the same. The code you will write is the same. You're going to just pass a function pointer or a function object to tell what's going to happen every time there's a scalar multiplication and every time there's an addition. And you will get different graph algorithms, I promise. So you do this once, and what do you find? You find 1 hop neighbors. Beautiful. OK, then I renumber them again with their indices and put it on my right-hand side. I do it again. Now what happens is I'm going to explore the neighborhood of 2 and 4, which means merging the columns of second and fourth column of this A transpose matrix. Now there's a little bit of magic. There's actually a collusion, meaning that vertex 7 is discovered by 2 vertices. Both 2 and 4 can discover it. And here you can see this in the matrix word. You need to do an addition operation. And in my definition, I chose minimum. As I said, I could have chosen something else. So 2 wins. And then I renumber and do it again. Another thing to point here is every time I do this, I might be generating some entries that are superfluous. That I don't need them anymore. Because look what's happening in this black and white chessboard-like shaded stuff. So 3, 5, and 7, they have back edges. For example, 7 has a back edge to 4, right? But I've already discovered 4. I don't need to rediscover it as part of this process. So, so there are 2 ways to do it. In the standard way, you do the multiplication, the output is generated, and you then prune it using this vector you've kept, which is all the stuff that you have visited so far. That looks a little inefficient. There's another way to do it. You use that parent's vector as your mask, and you say never generate anything that I already generated before. There's a long argument about in high-performance graph algorithm people on this pull-based algorithms, push-based algorithms. Let's not get in there. In matrix word, all you do is matrix vector product, and if you prune it afterwards, it's OK. It's embarrassing the parallel operation.
Are the entries in matrix and vectors really elements of a ring or not?
There are not. I mean, no. They can be whatever. I can be attributes.
I know they can be, but to do this is the min and
yeah. I mean, this is kind of contrived to the point that in practice, a ring or semi-ring or any algebraic operation is defined on a single set. I already abused it, where the matrices are Boolean and the vectors are integers. But that's just fine. The system runs perfectly fine as long as you obey some of the associative properties of these operations. I think that I found some math references on things like heterogeneous algebras, but sometimes you want to name these things in such that people can easily find them in Wikipedia. And we called it semi-ring, even though no semi-ring is defined in 2 sets. In fact, you can do it 3 sets. There's no reason why the elements of the matrix, elements of the vector, and the elements of the output should be from any 2 sets. It can be all different, as long as you define it properly. And that's fine. How do you do it in parallel? That's also pretty easy if you look at the matrix. Now, this is the one-dimensional vertex partitioner I told you about. So what do? I have 4 processors. The first 2 vertices go to the blue processor. The second 2 go to the red processor, and so on. And in the picture, it becomes one-dimensional cut of this matrix. That's why we call it that way. And how do you compute breadth-first search? Well, I mean, my local traversal of finding the neighbors I need to update requires no communication. I already own, as a blue processor, the edges that are outgoing from vertices 1 and 2, right? But I don't own any of the vertices that are 4, 7, 5 by construction. So I have to send data to them, letting them know that I've discovered them and they should update their distances, parents array, whatever they need to update. And then that will require the communication. So this is the second piece. And all-to-all communication practically among all processors. And it's likely going to use all the edges. So it's going to be pretty expensive. And then the recipients will update their distances and parents array. Great. Issues, load imbalance, I said earlier, potentially on certain graphs. This all-to-all is very expensive because it will cut all the edges effectively. And it involves every processor. When you have 10,000 processors talking to each other, all-to-alls don't scale very well. And a better way to do this is a 2-dimensional checkerboard distribution. You've already seen how to cut this. But I want to highlight one point. I would have taken a very long time to cut this graph in this manner without looking at the matrix. There is a structure. You see what's happening is the first n over square root of p processors, which is 1, 2, 3, 4, if you take the ceiling. Sorry, it's a 7-vertex example. It doesn't perfectly clear, but are collectively owned by blue and red. And it's not just randomly collectively owned. The way which one is blue, which edges are owned by blue, which one is owned by red, depends on the outgoing, the endpoints. If the endpoints are in the 1 to 4 range, red is the owner. If they're with the 5 to 7 range, blue is the owner. So that's the stuff that's going on. But for the matrix world, it's trivial. I don't need to think about those things. But what is the extra issue here? Now, if I'm the blue processor, I own vertices 1 and 2, fine. But I don't own all of their outgoing edges. So I own this edge to 4, this edge to 7, this edge to 5, but I don't own the edge that goes to 2, for example. So I need to do an extra communication to make sure that I own all the edges that I need to own to do my local discovery. And that will be this extra gathering process. The good news is it's not all-to-all, because I only need to gather data as the blue processor from the red processor. And similarly, the red processor will only need to gather it from blue. And the green and black will need to only gather from each other. In the large scale, only the communication happens in the processor column, what we call on this dimension. And in 2 by 2, it doesn't seem like a big deal. All you're saying is the red doesn't talk to black, and the blue doesn't talk to green. But when you're talking about 10,000, it's a big deal, because now you say out of 10,000, only 100 groups of 100 communicate. That's a big difference. And the rest looks awfully the same. You do another local discovery. You exchange the distances. Here again, the communication is limited. In the exchange distances function, you don't need to communicate with everyone. And this is easy to see if you ignore the breadth-first search fact, and all you're doing is matrix vectors. What is happening in matrix vectors? This vector, in practice, just think of it this way. it's right here. It scales the columns, and then local updates, and then there is a exchange in the row dimension to generate the output. I should have put in a longer picture there, but the second communication is also not all-to-all. It's only within processor row. Only, in this case, the red and the green will communicate, and the blue and black will communicate. And this is scales much better, even though initially it's a little slower. So you know how to do breadth-first search now with sparse matrix, sparse vector multiplication. And why is the matrix sparse? Because in many graphs, it's usually sparse by definition. Most interesting graphs are sparse. Some are dense, and I'll talk about them. And why is the vector sparse? Because when you do breadth-first search, the active frontier is not the whole set of vertices. It is whatever you're exploring. Just to remind people, this was the breadth-first search. Initially, this frontier is only 1. Then it's only 2 and 4. And then it's only 3, 5, and 7. In many cases, it is sparse that it doesn't involve all the vertices. So I'm going to talk about all-pair shortest path, and that will be the only dense matrix algorithm I'm going to talk about today. Did anyone hear about this algorithm, all-pair shortest path algorithm by Floyd and Warshall? OK. So that's the textbook example. It's really nice. It's proof. I don't have the time or the interest to do it. But it took a lot of years for people to discover this algorithm. Because when they first thought, oh, we want to find the shortest paths between any pair of reachable vertices, it looked like a, n to the fourth problem, where n is the number of vertices. It turns out it's not. If you do your induction scheme correctly, it's an n to the cube problem only, and only if you do it that way. So this is written in a triple nested loop, where you shouldn't be changing the outer loop, because that's the correctness of the algorithm. So what you do is you relax the distances. Basically, you say, if I'm trying to find the shortest path, the shortest distance between vertex I and j, first I'm going to see what is the shortest distance between vertex I to vertex 1, plus the shortest distance from vertex 1 to vertex j. And I'm going to keep that. And then now my middle vertex will be 2. Then it will be 3. OK? But you can't just do it if you don't go in this 1, 2, 3, 4, 5 order. It needs to be a particular order you have to follow. You can probably do it in reverse order, but you can't just shuffle them all over. So there is an induction sequence you shouldn't be parallelizing. That's fine. So what does the algorithm look like then? The algorithm looks like really doing outer products in matrix terms. You just take the outer product with the first column, first row, update the whole matrix. Take the second outer product in the second k equals 2 case, second row, update the whole matrix. The important part is update the whole matrix. Unlike LU decomposition, you don't just update the trailing part, the arrow one. And this algorithm is a little bit of a problem because outer products are memory intensive. They only do n-square operations and update n-square entries. And that's not a lot of, that's not a great use of memory hierarchy. And you'll see in the slides that it actually uses GPUs very badly. So there's an alternative algorithm that's not taught in textbooks. It took me a while to find this. It's by Clean. You can find this in automata textbooks. Clean's algorithm for push-down automata. That's one version of it. Really, it solves the all-pair shortest paths. Now, I'm not going to prove this algorithm because it actually takes me 45 minutes to convince myself that it's correct again. Every time I look at it, the way you decompose this problem first is you see your set of vertices as if they're in two classes, V1 and V2. You can choose that any way, but I'm going to say that V1 is the vertices in the first n over 2, and V2 is the second n over 2. And then A is the set of edges that are within V1. And D is the set of vertices within V2. And B and C are the interset vertices. If you look at the adjacency matrix, this is what it would be. A, B, C, D. Or in this case, this section would be A. This section would be C. Pretty simple. Right? OK. And then you run this algorithm. First, you recursively call yourself and find all the shortest paths within A. And then, using that information, which by induction, you'll see that you already found the correct shortest path in A. Now I'm going to find the correct shortest path by, for example, for B. So what do? I update B to the shortest paths, stitch to the shortest path in B. I multiply these matrices, except that every time I do an addition, I find a minimum. Every time I do a scalar multiplication, I do the addition. This is the so-called the tropical semi-ring, the min plus semi-ring, to find shortest paths. And you'll see that what you're doing essentially is this same relaxation operation that is defined here. You try to find the minimum between, I know my distance I to j, but I also want to compare it from going to a kth vertex as an intermediate. And I'm going to see if going through the kth vertex is any shorter than the distance I already know about. And magically, matrix multiply does that under the covers when you do mins and pluses.
Have we seen this? Have they seen this before in the form of cache-oblivious matrix multiply?
In this class?
In this class, they have seen that.
Oh, cache-oblivious. Yeah, it's strangely a cache-oblivious algorithm too. But I don't. Yeah, this is a very A, cache-oblivious, and actually B, very cache-friendly and perfect for certain machines. And this example, I tried to continue a couple of slides. You can play with it later to see what's going on. But the easiest way to prove this thing is really look at the regular expressions and do a little bit of elimination on the regular expression and to see that it's all correct. So what is the result? Why do I go to this, contrived example of taking something that's already a little bit complicated and even making it a matrix-based algorithm to make it further complicated? Well, this is the motivation. So the red line, no, the green line is when I implement the standard algorithm in CPU. Fine. The red line is when I implement the Floyd-Warshall, the standard algorithm on GPU, and it doesn't give me any speed up because it doesn't use the machine properly. It's just the arithmetic intensity of these outer products is 1. So there's no benefit from GPU, at least on that generation. There's a little bit of more bandwidth these days. Maybe you'll get 3 times faster, 4 times faster. That's all about it. But if I just use this recursive cleans algorithm, even with the wrong matrix multiply, unoptimized matrix multiply, I got like 60, 70 speed up. That's crazy. But then what we did is we went to the optimized matrix multiply implementation, changed a couple of things because I need to change the semi-ring to be min plus, right? And boom, you're like 480 times faster than your baseline GPU number. So that painful exercise, mental exercise, I think this pays off in this case. You can find the result down there. It's pretty old. But then you can use the same idea and even incorporate some communication avoiding things to run this in distributed memory. So we then extended this work to say, how can we do this in distributed memory? And there are 2 secret sauces there. One of them is every time you do matrix multiply, your matrix multipliers are getting smaller and smaller because of the recursion. So you have to use replication. I don't know if you've heard about communication avoiding algorithms. They do some judicious level of replication, C times, and the benefit of that, it will reduce the bandwidth in a square root of C times. And then latency also gets reduced in some cases. But we wanted to find optimal algorithms both in the amount of bandwidth, which is the number of words that you communicate between processors, and latency, which is the number of messages that are sent between processors. And to do that, we had to answer a question and switch it at the optimal time, which is every time I recurse, the problem size gets smaller. I have 2 options. I can keep all processors busy and give them smaller and smaller pieces. Or at some point, I can say that this is getting too many messages. I'm going to let these processors, only a subset of them, be active and let them rest, sleep, so that I don't shrink my problem size. And there's an optimal switch point that will minimize both latency and bandwidth. More on the paper. But the result is, if you don't use communication avoiding tricks, C equals 1 is the standard matrix multiply. For small problems, you actually start getting slowdowns after a while. But if you use that extra memory you have because you're recursing on a smaller problem by avoiding communication, then you will scale pretty much on any size problem. That was pretty cool. Questions? OK. That is actually going very well. The next algorithm is fairly simple. It's not going to take too much time. But it's nice because when I first talked about this with, when Jim was sitting, I was a guest lecturer in CS294-73. Now I'll be co-teaching it. Jim said, Luby, which Luby? Like Michael Luby? I said, yeah. So that was my office mate in grad school. He was here. So anyway, it turns out Michael Luby was a grad student here. And he discovered this algorithm pretty much when he was here. Here's a maximal independence set. What does it mean? First, I need to define what's an independent set. It's a set of vertices that are not neighbors of each other. That's that simple. 4 and 5 are form an independent set because they don't have neighbors. Great. They're not neighbors of each other. Sorry, they do have neighbors. But OK, what is a maximal independent set? A maximal independent set, I give you a set of vertices that are independent, and I ask you whether you can increase this cardinality of that set. You're not allowed to remove the first set of vertices I gave you. Like, I gave you 5 and 4. You can't delete them. You try to add something to it. If you can't, it's maximal. It's a local maxima, right? In this case, it turns out you cannot add 5 and 4 because whatever other vertices are in there is a neighbor of either 5 or 4. But it is not maximum because if you were allowed to delete 4 and 5 and start from scratch, you would find that there is a set of 3 vertices that are independent from each other. And that would be your maximum set. So finding the maximum is MP hard, and most people don't deal with that. Maximal is still a very useful property. This is used in, for example, when people choose their seed sets in algebraic multigrid, their solver technique. They choose the stuff that's independent so they can form aggregates around it. I'm actually lying a little bit. They use a maximum independent set distance 2. So they want not only them to be not neighbors, also their neighbors to be not neighbors, so that the aggregates are independent. But there are a lot of other use cases of this. We mostly care about maximal. The serial algorithm is, I would call it trivial. You iterate over all vertices. You add, for example, the first vertex to the set, and then you check 2 and see if any of its neighbors is in the set already. Well, for 2, that's the case, so I can't add 2. I can't add 3. I can't add 4. But 5 I can add, because 5's neighbors is not in the set I have added. And I linearly continue this way. I get 3 vertices. Perfect. It's a maximal independent set. By coincidence, it's maximum too, but just pure luck. The problem with this algorithm is, even though it's pretty fast, linear time, its critical path that I described before, span, is order n. You go sequentially. And Michael Luby said, well, there's an easier way to do this in parallel, at least if you use randomization. So I'm going to do this. Forget about the long text. It's actually pretty trivial. Everyone tosses generates a random number. Okay? Then everyone looks at their neighbors and looks at the random numbers their neighbors generated and compares it with their own random number. If they generated the smallest number among their neighbors, they add themselves to the independent set, which is the set S. So initially, everyone is in the C set, which is the candidate set. Right? So, and now, if I am chosen a random number smaller than my neighbors, I add it. And this is reflexive, because my neighbors also will get my neighbors, so there cannot be any accidents that both of us accidentally add each other. Right? And now 1 and 5 win the lottery. They add themselves to the independent set. But I'm not going to rerun this algorithm in the whole set. First, what I'm going to do, I'm going to delete 1 and 5 from the candidate set. Not only 1 and 5, and also the neighbors of 1 and 5 from the candidate set. So the candidate set will only have 6 and 8 left, and they're going to run the lottery again among each other. One of them will win. 8 won, done. You can prove with some arguments of distributions that this is going to take at most log n steps. So you increase the work a little bit, logarithmic, not that important probably, for a cheap algorithm. but your parallelism is significantly increased because this algorithm is critical path only in the number of iterations. So it's a, you have order and parallelism now. It's pretty good. And in practice, it runs pretty well too. How do you do this in GraphPlus? So this GraphPlus is the formalization of the concept that you can do graph algorithms in the language of matrices as long as you define these semi-ring operations, the scalar multiplications and adds yourself, or some system defines it for you. So you have flexibility. And you can learn more about it in GraphPlus, but this is an actual code that it compiles and runs. So when you try to gather the probabilities of your neighbors, what you do is a matrix vector multiply. So the vector there has as many non-zeros as your cardinal candidate set, the C set, initially everyone, right? And from that candidate set, you get the probabilities they generated. And that gathering operation is a matrix vector multiply. And now you compare it with yours. It's kind of this apply and element-wise multiplies and adds is the comparison that you do with them. And these are all, those parts are embarrassing the parallel, no communication happens. And for the next attempt for any communication, important piece is now you need to delete not only yourself, the ones that won the lottery, but also the neighbors of the people that won the lottery. And for that, you have to let your neighbors know that they should delete themselves. And you do another matrix vector multiply for that. That's the second matrix vector multiply. But the code, this is the bulk of the code. Everything else is declaration. It's not long, and it's mostly comments. So what did we learn? We optimize one primitive, sparse matrix, sparse vector multiply, and we get multiple algorithms fast. In fact, I'm going to talk another one, between centrality. And the reason I'm going to talk about it is not to hammer the matrix vector product. It's also to show matrix-matrix product has more parallelism and has a richer semantics, can be used to speed up some really cool algorithm called between centrality. Question? OK. I'm surprised people are awake. That's good. So between centrality is, centralities are...
Pictures. They're really good now.
Pictures. Yeah, I mean, so I asked my advisors in the first job talk I was going to give, so what should I do? I said, well, I asked that question to my advisor. He said, his advisor was Bob Tarjan that I talked to you about. He said, use a lot of pictures, he told me. So I guess you should just use a lot of pictures. And it doesn't need to be job talk. So in general, it works. So centrality measures are important measures on graph. They usually are defined on lots of different ways. And some of them are based on eigenvectors. Some of them are based on degree. Betweenness is one of the most expensive ones, but one of the most robust ones. It's based on shortest paths. So you answer the question, among all the shortest paths in this graph, what proportion of them are passing through me? And if many of them are passing through me, maybe I'm an important person, important entity, important brain cell, whatever you're trying to find. OK. That part gets a little interesting. So somebody needs to remind me what this Greek letter is pronounced. This guy. I'm too embarrassed because I haven't looked. Sigma? OK, good. One day I will learn these things. OK, so the way this is defined is sigma st is the number of shortest path between vertices S and T. Sigma st v is the number of such vertex path between S and T that pass through v. So the definition of between centrality for a vertex v is that ratio among a sum over all pairs st. So you basically normalize based on the paths. Why is this normalization there? If S and T has 3 equally short paths between them, parallel paths, you don't want to reward the vertices in between those paths 3 times, right? If there's a vertex in between S and T, but he's on 3 of these paths, you don't want to be giving him 3 times more between centrality score. Every S and T pair should be influencing the between centrality score equally. That's why you do the normalization. You could do this by the algorithm we talked about, all pair shortest paths, run it, store the result, compute between a centrality really fast. Except it's an overkill because that algorithm is n-cube. For sparse graphs, you should be able to do better. And the chances are you're not going to be able to store this. I can solve between a centrality on graphs with 10 million vertices, there is no way I'm storing a 10 million by 10 million all-pair shortest path output soon. Right? So that's the trick. Instead, Brandis, did I not list his name? It's there. Brandis's algorithm, Ulrich Brandis came up with this ingenious algorithm. I'm going to describe his algorithm in, again, matrices and vectors in parallel. So the way he did is, I can do breadth-first searches and accumulate things back in a back propagation stage to abuse the name using deep learning significantly. And I can make sure that all these normalizations are properly accounted for. And I will count the between centrality scores for any vertex that in between S, the starting vertex, to anyone else that I will go. So let's start with the example, 4. I have to do this for every vertex, one after the other, to get an exact between centrality score. Because now I'm going to build the shortest path from S, from 4 to everyone else. But it turns out you don't actually need to do this to get a good estimate. If sampling some starting vertices is an unbiased estimator. So it's fine, as long as you sample enough. So anyway, those are side effects. So you pick 4. You start doing breadth-first search. I'm going to keep track of every set of vertices in the level. So this T is going to initially have only 4. I will discover 1 and 3. I'll keep them in T2. And from there, I will discover 2 and 6. I'll keep them in T3. Right? Why am I keeping track of that? Essentially, what T is encoding is the breadth-first search tree, layer by layer. It's important because when I go back, I don't want to be exploring vertices that are not in the tree. And it's going to become apparent. If you don't get this algorithm at first, that's fine. It took me 3 times. The second trick that you do is if there are parallel paths that pass through that vertex, you encode them. Now look at 2 listed in vertex 6's location. So why is there a 2 here? Because you can reach to 6 either by going from 4 to 3 to 6 or 4 to 1 to 6. So there's 2 parallel paths to get there, and they're both distance 2 if it's an unweighted graph, which is the example I'm running you. So you have to keep track of it so you can divide it later, the contributions with 1 over 2. That's all. And that's about it. The Q is really not a fancy data structure. Q is just the sum of all the columns of T. That's down there. It's the number of shortest paths that reach to that vertex. So for example, Q of 6 is the number of shortest paths that come to 6. It's 2. And every other dot means 1. I just didn't.
How did the shortest part of this get?
I mean, I'm giving you only the unweighted case. So every hop is 1. So that's the shortestness. If there are weights, you would run a Belmont Fort instead of a breadth-first search. But I was in SC, and somebody talked about how to do that in semirings just as fast. Edgar Solomonic I was the session chair there. So it's doable. But I'm going to open up a parenthesis. So what I said is you're going to do this operation, breadth-first search, from every starting vertex. Or I said many starting vertices to get a good estimate. You need to do if you have a 10 million matrix, you need usually 1% of sampling. We're still talking about 100,000. That's a lot of things. But what is the memory requirements of this thing? It's not much. You need to keep this T, which is on the order of vertices. And usually your edges is about 100 times more than your vertices. So you can keep 100 such T's in parallel, wouldn't asymptotically increase memory at all. And if you have a graph that's a little smaller, 10 times smaller than your memory, you can keep 1,000 such T's. Right? So that's the benefit. Why do 1 at a time? This has some parallelism, but this is not so parallel. So I can do many explorations in parallel. Instead of choosing 1 starting vertex, I can choose 1,000 starting vertices. And that's where we go from sparse matrix, sparse vector to sparse matrix, sparse matrix. So now instead of doing A transpose to 1 column, now I'm going to multiply with a tall, skinny matrix. It's not that skinny. It has 1,000 entries, probably, on the row dimension. For each one of these columns in B is a starting vertex. Now I'm simultaneously exploring from 4, 1, and 3. And with one matrix multiply, I will find the first top neighbors of everyone in parallel. And then I will do the same trick. I will move this to the right-hand side, do it again, and prune the previously discovered ones. Continue until all the breadth-first searches are done. So the magical part of this is you won't know when you implement A transpose B with sparse matrix multiply what you're doing, like how much parallelism you're exploring on the graph. But you encapsulated 3 levels of parallelism without noticing. One is the parallelism over different searches, the different starting vertices and different parallelism, which is on the rows of B. One is the set of vertices in each frontier, in each breadth-first search frontier. And that you encoded in the inner dimension of matrix, the rows of B and columns of A transpose. And for each element in the frontier, they each have their adjacencies, the set of edges outgoing from them. That's the third level of parallelism, the edges of outgoing, and that's encoded in the rows of A transpose. And the matrix-matrix product will exploit all 3 without you knowing about it.
So let me answer my own question, because
Yeah.
I didn't communicate it properly. So the answer to my own question is a really simple question, which is, how do you know that you're getting shortest paths? And the answer is you're doing breadth-first search.
Yeah. Okay. I thought that, yeah, I didn't exactly know what, that's what we're doing, yeah.
Yes, breadth-first search guarantees that there isn't a shortest path, because you would have found it already. There's
For-
a shorter path.
For unweighted graphs.
For unweighted.
Yeah, exactly. Exactly. For weighted graphs, you do Bellman-Ford, and it's still matrix products or matrix. I should put Edgar's citation now that it's updated. Okay, here's it in GraphPlus. The first page is just a bunch of descriptors. I'll come back to it. Don't worry about this. The bulk of the computation is here, where you do the matrix-matrix product. So what do? You do multiply with the A transpose on a semi-ring that finds the breadth-first search tree. And in this case, it's just a standard add and multiply is fine, because I don't want the Booleans, because I want to be able to count the number of paths. Remember, if there are 2 parallel paths, I want the 2 to be there. So it's the integer standard field there that's going on. There's a couple of things. I don't explicitly transpose A. See, I pass A, and I just pass a descriptor that says, assume A is transposed, just like BLAS does. So this is more efficient instead of explicitly transposing it. And finally, here's the crux, the mask. I also pass the set of vertices that have been previously discovered, meaning that the set of vertices that I know the shortest path so far as a mask. And I tell the system, you do not need to compute the output on those guys, because I know them. And the syntax is kind of, you can learn the way you say that he needs to not compute stuff in there is encoded in how you type the descriptor in the previous slide. You tell, for example, structural complement, meaning that do not compute the things in the mask. You could have said, do compute the things only in the mask. That would be different. And this is how you encode the transpose. Unimportant details, unless you want to use the interface. But the bulk of the computation will happen in one line in the code. That's the most expensive one. And if it's properly implemented, it will be just as fast. OK, the timing is going really well. I'm not done. All I found was breadth-first search trees. Now I have to actually compute the between centrality scores. For that, I start the end of this breadth-first search tree. And the leaves of the breadth-first search tree is this T4, the last layer. Right? So because that's the last set of vertices I explored. And I start from them and go back. Instead of the A transpose X, I do AX, because now I use the reverse order of the reverse direction of the edges. So I'm going back. Now I say from 5 and 7, who came, which vertex came to 5 and 7? 2. I follow the back edges. And I say, OK, so 2 is in between. This my starting vertex 4 and 5 and 7. So 2 gets 2 points for being in between 2 vertices. Boom, great. Now in the next layer, I'll use T3 that I stored previously, because that was the third layer in the breadth-first search tree. But I also will continue using 2, because it's from one hop up from 5 and 7. So Now I do the one more multiply. Sorry. Yeah. Here, from 2 and 6. 6 was also in T3. 2 came from the T4. And I do one more back step. Now, these guys will propagate their in-betweenness to their parents. 2 already had a betweenness score that of 2 it was propagating. It's going to add its own score. It'll propagate 3 to its neighbors, to its parents. And 6 will only contribute 0.5. And why is that? Because there were 2 ways to come to 6. So 6 can only contribute half score to its parents. And this whole operation, this proper divisions is taking care of that. So 2 is giving 1, 3, and 6 is giving 1.5. So 1 is getting 3.5, and the others get 0.5, and continue so forth. So you get all the updates of betweenness centrality, and then you apply this contribution to a global betweenness centrality vectors. You do it for the next batch of vertices again and again, and then finally get the correct answer. The backward sweep, the tally, is also implemented in similar ways. And the bulk happens in matrix-matrix multiply, again with a mask, almost the same stuff, except the semi-ring is different because now I'm not running in integers, I'm running in floating points because I need to keep track of 0.5s, 0.3s, or whatever. It's easy. There was one little thing that I said, yeah. And the masks tells you should stay in the breadth-first search tree and not explore any wrong vertices. All right, so that's for betweenness central. That's probably the most complex graph algorithm you might see in your life. But it's fun stuff. I'll finish this.
Remind me again, what's it used for?
It's to find influential entities usually.
Or hotspots is another way of thinking.
I wrote, yeah, that's fun. I wrote a code in a grad school class, in data mining class, about finding, DBLP, the database for computer science publications. And that data was available. So we did a topic modeling of, we modeled each paper based on its abstract into topics. It says this paper is about distributed computing. This paper is about cryptography. And then you can ask questions like, OK, who's the most influential person on this topic? Just run betweenness centrality. And it actually gave good answers. Well, you say machine learning, it said Michael Jordan, that kind of stuff. It wasn't bad. One example. Export finding or hotspot finding. In Brain, you find stuff that's kind of, if you take that piece out, most of the connections would disappear. So you probably don't want to hurt that piece of your brain. Counting triangles. So this is used in clustering coefficients. I'm not going to preach its use. And clustering coefficients is used to classify graphs into classes. But it's a nice academic exercise. How do you count triangles in a graph? So the way an algorithm I really like, and most of these algorithms are flavors of each other. All you're doing is you need to find all the wedges. A wedge is a triangle that doesn't close. And then once you find all the wedges, you can see whether they close or not. If it closes, you count. Otherwise, you don't. And most of them are flavors of this. Cohen's algorithm is a smart one. It only counts wedges twice as opposed to stupidly 6 times. If you have a triangle, you can, and if you just list all the wedges, you will count each triangle 6 times. And by just putting an ordering in the vertices, numbering them, and only counting wedges where the hinge, the middle guy, is the smallest numbered guy, so you will not count the other 2 orientations of the wedge, which is still going to be correct. You just need to find one of them. So, but Cohen goes further and says, I'm not just going to randomly number these guys. I'm going to number them with increasing degree of vertices. Why? If you have a wedge where the middle guy is a high degree vertex, let's say this guy has 10,000 connections, well, it will be part of 10,000 square wedges. Well, that's a stupid idea because you're going to generate lots of wedges. Chances are many of them won't close. So to be memory efficient and computationally efficient, you want to only list the case where the wedges have the lowest degree vertex in the hinge. So that's what it does. Order by degree, only enumerate wedges on the hinge, and then it's all correct. It's because it's only going to change the number of wedges you generate as an intermediate. The counts are correct. Here's the magical linear algebra. So get your matrix. Assume you already ordered this by degree, whatnot. Split it into two pieces, L and U. This is not a factorization. It's just split it into two. L will have the lower triangular part. It will have the edges that go from high degree to low degree by definition. And the U will have only the edges that go from low degree to high degree. Okay? When you multiply L and U, you're essentially finding all the wedges where the hinge is the low degree one. Right? When you multiply L and U, you're going from high to low, low to high. Because a multiplication is really just an exploration. So you're stitching two edges. Now the output of L times U, B, it has all the wedges with the low hinge. And I just, that's what it is. And the counts of them. If there are two such wedges, it will have two. If there are three such wedges, it will have three. Perfect. And I finished this operation by checking whether that hinge that wedge closes or not. So to find that, I get the output B, and I do an element-wise operation with the original graph, A. And if there is an edge in A in that location, it will say that this triangle is closing. So otherwise it's not closing. Now the only problem is I double counted. I need to divide it by 2, but that's all. This algorithm not only counts, it also enumerates. If instead of doing a sum, I could have enumerated all the triangles. It's a little more memory inefficient, but who cares? So this is ingenious, and the whole bulk of the computation in GraphPlus notation is one line. You just, multiply. Instead of L, I'm using L and an L transpose because this is a, symmetric matrix or an undirected graph. And I just use one variable, L, that's both my first input and my second input. I also tell the system the second version, you transpose it. And my mask, because I do not want actually the system to generate any wedges where the closing edge of the triangle doesn't exist. Because I might be doing very inefficient work if I generate lots of wedges that do not close in the end. So by putting a mask to say that only generate the wedges where there is already a closing triangle, I basically tell the system that do it as efficient as it is. You can if you know the algorithm to do this matrix multiply in a pool-based manner. So that's about it, and all the examples I'll say. So I'm going to do an inverted lecture and, in some sense, put all the motivations at the end. Now you've seen all the examples. But I didn't show you lots of performance data. I showed a little bit in all pairs shortest paths, but that's about it. Why do we do this? The claim here is that graph algorithms have lots of parallelism, but it can only be exploited in the right level of abstraction, and the matrices and vectors is that abstraction. And here are some of the reasons. You open your textbook in traditional graph computations, you'll see a stack that you used for breadth first search. It doesn't need to be, but nobody knows. And the first attempt to parallelize it was like, how do I parallelize a stack? Well, you don't need to. The correctness of breadth first search has nothing to do with the stack. So the matrix view will expose any parallelism that's in there. That's already. And it will, instead of having data-driven computations, you'll have fixed communication patterns. You know when you're going to communicate in sparse matrix, sparse vector multiply. First the row order, first then the column order. You can overlap them. You can do whatever you want to optimize them. Similar for data access. So you think that the data, the locality of reference doesn't exist. But once you cast this in the matrices, the system is allowed to reorder the matrices and to get big blocks with lots of non-zeros in there that will run much faster on cache-based machines. So you can get a locality from there. You wouldn't be able to mine from the graph itself, but you would mine from the matrix properly. And essentially, you're moving a latency-bound problem to a bandwidth-bound problem by doing linear algebra is forcing you to do bulk communication, bulk operations. So you're still not going to get away from the data movement, the bandwidth part, but you can always buy more bandwidth. The theory is you can never get less latency beyond the law of physics. So you might, and there's a little picture. The picture is not important. Some of the primitives that we've explored, we haven't explored indexing, but it's very useful. But the more important point is a quote that I like to steal from Charles Van Loan. This is the guy who wrote some of the most encyclopedic linear algebra books. It's not even a book, Matrix Computations. It's like a real great reference. I think did he pass away? Is Charlie alive? I think he retired. There was a retirement.
Yeah, there's a difference.
Yeah.
Turns out.
Sorry. So this is a nice quote from him. My mission is to build a linear algebra science to the extent that vector level thinking becomes as natural as scalar level thinking. And you'll see that no professional linear algebra person will think about inner products when doing matrices. They will think about columns and vectors. And similarly, thinking like a vertex is just as low level as thinking like single entries and matrices. And matrices and vectors is essentially that vector level thinking. That's going to give you performance and productivity. Some examples of different semi-rings and different problems that they're used in for just reference. And finally, you've seen half of these examples, but there's more. So some of these problems and their dependencies in matrix operations I tried to list. I just listed the sparse ones, but there's the dense ones. The things that we haven't covered is connectivity, graph matching, page rank, clustering algorithms. We haven't talked about them, but they nice to map to linear algebra as well. And that's all about it. Thank you for your attention.
Now we have a couple of questions.
I should have put my email. Some sense.
Put it on the title page of your slides.
Yeah, that's pretty much what I'm going to do. Cool. Thanks so much. And if you have any, you can email. This doesn't stay.